Welcome to Lesson 3 of my Red Pill course on calculus, where we will discuss the concept of continuity. Through our new view of the universe that we gained in Lesson 2, we have discovered that there are unlimited numbers and non-zero infinitesimals in R. We achieved this by introducing a new primitive notion, the unary predicate standard, and postulating three new axioms which we have called transfer, standardization, and unlimited reals. This has also given us a new view of the real number line, which, if we combine different scalings, now looks like this. The standard numbers are shown here in blue, the non-standard numbers in red. The purple sections include both standard and non-standard numbers. The positive, unlimited numbers on the far right are those that are greater than all standard reals. The positive, limited numbers are those positive reals that are less than or equal to some standard real. There are corresponding limited and unlimited numbers on the negative side. The infinitesimals are those numbers whose absolute value is less than any positive standard real. All real numbers that can be defined in conventional calculus are standard and therefore limited. This is our plan. In this course, we will use infinitesimals and unlimited numbers to define important concepts of calculus, such as continuity, derivative, and integral. We will first define these concepts for the standard case, that is, for standard functions and standard arguments, and then extend them to the general case by standardization. When proving conventional theorems, we can always fall back on the standard case. The general case follows by transfer. In the following, the calligraphic capital F denotes the set of all real functions, that is, all functions whose domain and range are subsets of R. Recall from Lesson 2 that anything we can define in the language of conventional calculus, possibly with standard parameters, is standard. For example, the sets R, F, and the Cartesian product F cross R are standard. If f is a real function and standard, then the domain of f and the range of f are standard. For any standard set A and each possibly external predicate phi of x, there is the standard subset of A obtained by standardization with phi of x. That is, the standard subset of A whose standard members are those that satisfy phi of x. Note that the non-standard members of the set do not necessarily have to satisfy phi of x. Recall that external predicates are generally not set-forming, which means we cannot use them with the axiom of separation. But we can always use standardization and thus obtain standard sets. What is a continuous function? Loosely speaking, a continuous function should behave well in the following sense. A small variation of the argument induces a small variation of the value of the function. If we look at the graph of this function f, at a point A, for example, a small variation of the argument a induces a small variation of the function value f of a. But what does small mean exactly? Since the absolute value of an infinitesimal is less than any positive standard real, in particular less than a half, a third, a quarter, and so on, there is an obvious option for the standard case. If we consider only standard functions and standard arguments, remember that all conventionally definable functions and numbers are standard, so if we consider only standard functions and standard arguments, We can specify the idea of continuity as follows. An infinitesimal variation of the argument induces an infinitesimal variation of the value of the function. We cannot recognize infinitesimal variations in the figure unless we use a magnifying glass with an unlimited magnification factor. More precisely, the definition is as follows. A standard function f is continuous at a standard point a in the domain of f, provided that for all x in the domain of f, if x is infinitely close to a, then f of x is infinitely close to f of a. We can also express this equivalently as follows. For all infinitesimal delta, if a plus delta is in the domain of f, then f of a plus delta is infinitely close to f of a. This definition seems at first to be relevant only for standard functions and standard arguments. However, it can be generalized very easily. As we will see, in a certain sense, it is actually sufficient to look at the standard case. We therefore start with the definition of a predicate S-cont that characterizes continuity in the standard case. We write S-cont of A and say f is S-continuous at A if and only if f is a real function and A is in the domain of f, and for all x in the domain of f, if x is infinitely close to A, then f of x is infinitely close to f of A. Then we define cont as the standard subset of f cross r obtained by standardization with the predicate S-cont. That is, as the standard subset of f cross r whose standard members are those that satisfy S-cont. We illustrate this in a diagram. The standard members of the set f cross r that satisfy S-cont are completed by standardization to form a standard set. This standard set cont also contains non-standard members that do not necessarily satisfy S-cont, but which have the same conventional properties as the standard members of cont. We sometimes call definitions like this implicit definitions, because we can only read the characteristic property of the standard members from the notation. Although the defined set also contains non-standard members. We say that f is continuous at A if and only if the ordered pair Fa is a member of cont. In this case, we also write cont Fa. F is continuous means that f is continuous at each point of its domain. Why is this implicit definition of continuity, based on S-continuity, useful? Suppose we want to prove that a given internal statement phi of x1 to xn with standard parameter cont holds for all x1 to xn. We can proceed according to the following proof schema. Show phi of x1 to xn for all standard x1 to xn. Here we can use S-cont instead of cont because all parameters are standard. Then, by transfer, phi of x1 to xn holds for all x1 to xn. In other words, to prove conventional theorems about continuity, it is sufficient to prove the standard case and use S-continuity. The general case then always follows by transfer. A trivial example. For all real numbers c, the constant function that maps x to c is continuous. Intuitively, this is clear because there is no variation of the function value at all. But let's confirm the continuity of fc using our definition. For all standard reals Cx and any infinitesimal delta, fc of x plus delta is infinitely close to fc of x, since all function values are even equal. That is, for all standard reals Cx, fc is S-continuous at x. Hence, for all standard reals Cx, fc is continuous at x, because for standard parameters continuity means S-continuity. This is an internal formula with standard parameter cont. Then, by transfer, for all real numbers Cx, fc is continuous at x. In this example, fc is also S-continuous for non-standard Cx, but in general, continuity and S-continuity are only equivalent for standard parameters. We can also prove the following proposition, which shows that continuity is preserved when we add, multiply, divide, or combine continuous functions. For all fga, if f and g are continuous at a, then f plus g is continuous at a. If f and g are continuous at a, then f times g is continuous at a. If f is continuous at a and 0 is not in the range of f, then 1 over f is continuous at a. If f is continuous at a and g is continuous at f of a, and the range of f is a subset of the domain of g, then g after f is continuous at a. The proofs all follow the same principle. Show the assertion for all standard parameters. Here we can use S-continuity and the calculation rules for infinitesimals. Then conclude by transfer that the assertion is generally valid. As examples, we prove B and D. Statement B is, if f and g are continuous at a, then f times g is continuous at a. For the proof, we define epsilon 1 as f of a plus delta minus f of a, and epsilon 2 as g of a plus delta minus g of a. For all standard fga and all infinitesimal delta, if f is continuous at a and g is continuous at a, then f of a plus delta times g of a plus delta is equal to f of a plus epsilon 1 times g of a plus epsilon 2. We multiply this out and get f of a times g of a plus epsilon 1 times g of a plus f of a times epsilon 2 plus epsilon 1 times epsilon 2. Since f of a and g of a are standard and thus limited, and epsilon 1 and epsilon 2 are infinitesimal, the last three summands are infinitesimal. And the total sum is infinitely close to f of a times g of a. So the standard function f times g is S-continuous and therefore continuous at the standard point a. This means that assertion B holds for all standard fga. Then, by transfer, assertion B holds for all fga. This example shows that continuity and S-continuity are not necessarily the same for non-standard parameters. In this case, f of a or g of a may be unlimited, and then the terms marked in yellow are not necessarily infinitesimal. Therefore, f times g is not necessarily S-continuous at a. Statement B, however, is about continuity and is generally valid. Statement D is, if f is continuous at a and g is continuous at f of a, and the range of f is a subset of the domain of G, then G after f is continuous at A. To prove this, let FGA first be standard. Then G after f is also standard. By premise, for all x in the domain of f, if x is infinitely close to A, then f of x is infinitely close to f of A, because f is continuous at A. And then g of f of x is infinitely close to g of f of A, because f of A is standard and g is continuous at f of A. Hence, g after f is continuous at A. The general case follows by transfer. Another example is the following proposition. For any natural number n, the function fn, which maps x to the nth power of x, is continuous. We proved this by mathematical induction. In the base case, f1 is the identity function on R, that is, the function that maps each real number to itself. For any standard real x and any infinitesimal delta, f1 of x plus delta is x plus delta, and this is infinitely close to x, which is equal to f1 of x. Hence, for all standard x, f1 is continuous at x. This is an internal formula with standard parameters f1 and cont. Then, by transfer, for all x, f1 is continuous at x. The induction step follows because fn plus 1 is equal to fn times f1, and products of continuous functions are continuous. As a consequence, we obtain two corollaries. First, any polynomial function is continuous. This follows by mathematical induction. Second, any rational function is continuous. This follows because a rational function is a quotient of two polynomial functions. We now come to a proof that is typical of non-standard analysis. Bolzano's theorem states that for any real function f that is continuous on the closed interval from a to b, where a is less than b, if f of a and f of b have opposite signs, then f has a zero in the interval from a to b. We assume that f of a is negative and f of b is positive, without loss of generality, because otherwise we could simply consider negative f. Let f(a)(b) first be standard. Let n be a natural number and xi the points a plus I times b minus a over n, for I from 0 to n. The xi define a finite equidistant partition of the interval from a to b. We define k as the minimal I for which f of xi is non-negative. We know that k is at least 1 and at most n, because f of x0 is negative and f of xn is positive. Furthermore, by definition, f of xk minus 1 is negative and f of xk is non-negative. F therefore changes between xk minus 1 and xk from negative to non-negative values. Now let n be unlimited, which means that xk minus 1 and xk are infinitely close. We know that xk is between the standard numbers a and b and is therefore limited. By taking the standard parts, we conclude that the standard part of xk is also in the interval from a to b. We define x as the standard part of xk and claim that f of x is equal to 0. By construction, xk minus 1, xk, and x are infinitely close. Since f and x are standard and f is continuous at x, f of xk, f of x, and f of xk minus 1 are infinitely close. Since f of xk is non-negative and f of xk minus 1 is negative, the absolute value of f of xk is less than f of xk minus f of xk minus 1, and this is infinitesimal. Hence, f of xk is infinitesimal, and hence f of x is infinitesimal. Since f and x are standard, f of x is standard. Hence, f of x is equal to 0. The general case follows by transfer. As usual, we can generalize Bolzano's theorem to the intermediate value theorem. Let f be a real function and continuous on the closed interval from a to b, where a is less than b. Then f takes on any value s between f of a and f of b in the interval from a to b. As proof, just consider the function fs that depends on the parameter s and maps x to f of x minus s. What are our fellow students in the blue pill course doing? They define continuity in the following way. F is continuous at a, according to the conventional blue pill course definition, if and only if f is a real function and a is in the domain of f, and for all positive epsilon there is a positive delta, such that for all x in the domain of f, if the absolute value of x minus a is less than delta, then the absolute value of f of x minus f of a is less than epsilon. Compare this with our definition of S-continuity. F is S-continuous at a if and only if f is a real function and a is in the domain of f, and for all x in the domain of f, if x is infinitely close to a, then f of x is infinitely close to f of a. As you can see immediately, the definition of S-continuity is logically simpler than the conventional definition of continuity. Instead of a nested epsilon delta dependency, we have a simple dependency with infinite proximity. It can be shown that S-continuity and conventionally defined continuity are equivalent for standard parameters fa. Our definition of continuity is also equivalent to S-continuity for standard parameters. Recall that we defined continuity through standardization based on S-continuity. Since the conventional definition is an internal formula, it is then, by transfer, equivalent to our definition for all fa. We note the continuity definitions in the red and blue pill courses are completely equivalent. As a conclusion of this lesson, we summarize the following points. The definition of S-continuity is logically simpler than the conventional definition of continuity. Continuity and S-continuity are equivalent for standard parameters. Conventional theorems can be proven by proving the standard case and then using transfer. Problems involving continuity can often be reduced to finite discrete problems. We have seen this with the example of Bolzano's theorem. In the next lesson, we will learn about a stronger version of continuity, called uniform continuity. I look forward to welcoming you there.